Let's recall what a diffraction grating or a Dirac cone in free space might look like. Something like this, and usually we take a single slit and we have the waves that kind of go through it and create a diffraction grating on a screen. But of course, we can make it into a cone by stacking them all up, and it makes a little grating like this. And we can define that sort of with this Shaw function right here, with a whole bunch of delta functions. Now, there's this Green's equation where we're trying to take a differential equation here and set it equal to some delta functions. And it turns out that the poles of this equation, basically the singularities here, are the solutions um, in Fourier space. So this allows us to find some specific solutions or eigenvalues. Well, let's go now to a regular flat space, so like Minkowski space where the curvature is zero, and then we're going to transform it to de Sitter space, so we get some curvature with it. Um, what's very interesting is that if we have a black hole or something, it has an ingoing boundary of this radius at the horizon, the event horizon. Um, if something whacks that event horizon, it creates sort of an ingoing wave, a gravitational wave that decays inward, and it creates some sort of a frequency. So it's hard to see it, but it kind of looks something like this, where you might have something sort of uh, off to the side here, and it just kind of hits one of these edges of the black hole, and it'll create some frequencies inside, but these decay inward. And that's kind of the property of gravitational waves is that they decay, interestingly. I do believe that when it goes inward for the black holes, you get an oscillation. So what happens, you get a WR here. WR. Oh, interesting. A real oscillation when something comes and hits that black hole. So that's what creates sort of this frequency. You could think of it sort of like hitting an instrument there. And so, but it goes inward because you're in a black hole. Um, but there's another event horizon, and that is in de Sitter space, which is our space, and it's our cosmic horizon where we look outwards, and as something crosses that horizon outwards, um, we can't ever see it anymore because of the expansion of space is so fast that anything outside of this radius RC 1 over h, basically we can't see it anymore. Well, it's really hard to get past that cosmic horizon, but we can't see past that. So yeah, so let's realize that during um, this outgoing boundary, we don't have a real frequency. So these frequencies, remember those poles that were the solutions to the Green's function over here? These poles right here, the delta functions. Well, those are frequencies, and so the frequencies in the poles in frequency space though. So what they give you is they give us the decay rates of gravitational waves, the poles in the frequency space. And that's because we are able to take a gravitation, well, here's just a regular propagator here, okay? And we could set the mass equal to 2h squared. That should be a gravitational wave. And so essentially we're able to get this situation down here, maybe over here. We derive a quantum field propagator like this. Um, we make it a graviton propagator like this. Um, and I believe we just use just a regular old graviton propagator equation here. As you can see, this is sort of a combination of these equations, and we essentially get the eigenvalues for this. This is in frequency space, and this is in regular space. Sometimes it's hard to connect these because they're in all sorts of different notations. And so really the key is to try to connect all the notations better together. But anyway, so we basically define that the poles here in frequency space are specifically the gravitational waves because that's how we define it with these equations right here. Anyway, so these, again, when you're outside the outgoing boundary horizon here, you don't get a real you don't get a real uh, frequency. That only happens when you're going inside. But you always get an imaginary frequency everywhere. And that's what causes the decay rate of gravitational waves. And that's what makes it so that way uh, they there's basically no gravitational wave network in real space because that would be this thing. This only happens inside of black holes, okay? So there's only really this complex frequency space over here, where there is, in fact, a network of gravitational waves. That would be this Dirac cone. So the Dirac cone sums up all the waves that have the decay rate of this thing here, which is the decay rate of the gravitational waves. Basically says that their gravity waves basically just become nothingness, and they kind of dissipate very quickly, so they don't really exist in space, very in real space. Like I said, no gravitational wave network. It only exists in complex frequency space. And so this is the Dirac cone. If we wanted to now add up all these waves, so we're creating sort of a diffraction grating. They're all exponentially decaying. And let's realize that if we look at a linear, we've so far been looking at a linear situation, just to kind of simplify the math up to this point. But if we have this setup here, essentially gravitational waves, even though they are in this um, complex frequency space, it's interesting because, well, they don't interact with light because they're not electromagnetic radiation there. There's no real frequencies. It's only imaginary space, complex space. Um, the decay rate is based off of H, which is interesting. It makes a big cosmic web everywhere because it's everywhere. And the propagators that we've defined here, they basically carry the information of the um, gravitational curvature. So these gravitational waves, they have propagators, and that's what this thing is. Okay, it's trying to basically send the information between the two different points, the two different um, the two different yeah, they're the poles in frequency space. So they're sending information between each other here, which is interesting. So these imaginary frequencies communicate between each other using gravitational waves in complex frequency space. That's the weird thing. All right, so this is a non-linear interaction, meaning we need to add uh, a, scalar here, and then we need to have basically the gradient times the derivative over here of the of the metric perturbed metric. But there's still a problem. We've still only set this system equal to 0, and I don't think that's right. I think that we would want to actually um, go further than that. But in the moment, let's just see what would happen. So the idea is that we're going to make this nonlinear. So we have to combine the effects of one and two gravitational waves and see what happens. If we do that, then all we do is we basically take a new constant c and n, add them together, and then we have those two, and then we have this. So it's just kind of basically summing two of these together. Right? That's fine. We have low fundamental modes though, because the problem is these decay really fast. So the only thing that might survive maybe is like m equals zero, the lowest fundamental mode possible. And that kind of makes a little bit of sense. We already kind of spoke about this in another video. Um, but yeah, these are kind of very subtly tuned to H. As you can see, this H is very important. Let's realize that the vacuum energy is also tuned to H squared over here. Um, and so we have this temperature of the universe, which is proportional to H. And so that tells us that the vacuum energy, or the vacuum frequencies, might be the driving frequency of this complex gravitational wave network in frequency space. Um, so that's very interesting. Um, what we're saying is that we might be able to even plug it into this particular value here or so. But this is essentially where it's sort of gotten to. We might have this driven frequency here that sustains this gravitational wave network in complex space. And it would lead to equations um, like this. This would be a solitonic core. Uh, so these things together would actually sustain this, even though it's a decaying, quickly decaying um, network. It's tuned to H, and so it's driven. So um, it's essentially a standing system. It's it's a feedback system, feedback loop. So it's never going to die out fully. And that's what leads to these solitonic core solutions, was that these gravitational wave perturbed metrics here, um, they seem to be sustained by the vacuum energy, the quantum waves. This is really weird stuff, guys. But this is essentially what the Dirac cone of gravitational waves. Well, the Dirac cone of the green function uh, holes in frequency space for the gravitational wave propagators. All right. Anyway, so good stuff. Hopefully that was made a little bit of sense, and that was fun. I'll see you around, guys.